Voy a hacer una breve introducción. Quisiera presentar al profesor Christopoulos y al doctor Montgomery, quien está aquí. La idea es pues mostrar este sistema alternativo, yo lo llamaría de diseño sismo resistente, bastante nuevo en México. Se usa ya, como van a ver, sobre todo en Asia, el sistema. Y la idea es que ustedes vean las ventajas o diferencias con otro tipo de sistemas, sobre todo que tenemos ahora una norma que nos lleva a soluciones diferentes a las convencionales. Primero quiero agradecer al Instituto de Ingeniería, obviamente, por darnos las facilidades de presentar este seminario o esta presentación, la difusión, y al SMIS, que ha trabajado bastante en la difusión de este evento, que creo que se sigue también por streaming, YouTube, y espero que les sea de interés. El profesor Christopoulos tuvo su grado de doctorado en la Universidad de California de San Diego en 2002 o 2001, y desde esa época es profesor en Toronto. Y el doctor Mike Montgomery estudió su doctorado con el profesor Christopoulos, obteniendo el grado en 2010, trabajando en el tema del empleo de estos sistemas de amortiguamiento, que en realidad muchos pensamos que es como un amortiguamiento de un fluido, pero en realidad es un sólido, y por lo tanto tiene no solamente capacidad de disipar energía como propiedad del fluido, sino también como un sólido. Entonces tiene esas ventajas. Lo va a describir obviamente el profesor Christopoulos. Lo interesante es que ambos han trabajado en la parte experimental y en la analítica. Es decir, no se trata solamente de estudios teóricos, sino experimentales, como vamos a ver. Así que con esto, sin más, el profesor Christopoulos, por favor, puede presentar su trabajo.
Okay, hello, can you hear me? Yes? Okay, thank you very much, Mario, for the introduction, and thank you everyone for being here today. It's a pleasure to be here at UNAM and to present a little bit of the work that we have been focusing on related to what we call solid-state dampers. You'll see in my presentation the reason we call it solid-state is to distinguish it from fluid dampers, which are more common in North America. It's quite the opposite in Asia. So just to distinguish them and to emphasize the differences. Part of my presentation, I like to use this picture here because I think that structural engineers have to, at some point, realize that adding stiffness and strength to structures has come to a limit, and we're finding now, especially on the west coast of North America, in the US and Canada, that the size of the members and the amount of reinforcement that is being used is becoming unpractical, uneconomical, and maybe we have to start really investigating what automotive and aerospace have done for a very long time. So you can see early stage cars which weighed about 100 to 200 times more than our cars today. And the reason that we don't have vibrations in these cars is there are typically about 400 to 500 small viscoelastic dampers everywhere in our cars. So this is just an example. I picked this out from a car manufacturer, and you can see all the locations in these cars where viscoelastic layers are being used. So one of the things to realize viscoelastic damping, one of the advantages we have is we can constrain it between structural members. And when the structural member is deforming, what happens is it induces a shear deformation and a shear stress inside the viscoelastic material, which allows us to basically dissipate energy while the structural member is fulfilling its function of stiffness and strength. So again, we are sort of late in the game, but all of these industries rely heavily on damping in order to achieve the type of efficiencies that we see in these. So what is viscoelastic damping? We're using a highly engineered polymer, which basically is then bonded rigidly to steel. And by combining this in different ways, we actually are able to generate shear straining in the polymer as basically the steel plates move relative to each other. So here I'm illustrating a damper that is a little bit, has multiple layers. And you can see here that when we pull on the damper, we are going to induce shear. So as I mentioned previously, any relative motion between this plate and these two plates is going to be inducing shear strain here. So now our goal is going to be, where do we position these two extremities in a real building in order to achieve the most efficient damping? And here I'm also illustrating the polymer chains, because again, I want to emphasize that the damping is provided at the molecular level. It is not like a device, like a fluid piston, where you have to move fluid inside the damper in order to produce the damping force. This is produced at the molecular level. And if you want to think about it, the best way that I think about it is it's friction, intermolecular chain friction. So as I'm pulling on this and stretching it, I'm basically creating friction and heat generation inside the polymer, which then dissipates energy and transforms mechanical energy into heat. So can you please play this video? Yeah. Okay, so you can see here that this is in the lab. When we look at viscoelastic materials, you can see here in a non-contact thermal camera that the material is heating up, and this heat is basically producing, this heat is then radiating either into the steel plates or into the atmosphere. But the key here is that this energy, this heat energy, is basically the transformed mechanical energy, and therefore we are extracting energy from the mechanical system and providing damping. And the other thing that is important to see here is if we analyze the force deflection response of this material, we are going to see that there is an elastic component, K times the displacement, plus a viscous component, a linear viscous component, which is a constant C times the velocity. And this exhibits this inclined elliptical hysteresis, which has a stiffness associated with it, and also this area underneath this hysteresis is the damping as well. Okay, so we're going to use these properties for one, to couple structural elements with the stiffness, and for two, to dissipate energy with the damping constant. So I just want to give you a little bit of history of viscoelastic dampers. First, just to look at the different configurations where we can use them. We can use them here. I'm going to talk today more about concrete buildings. This is instead of a coupling beam, we will put the damper in. This is in a built structure as a coupling beam. These are outriggers. These are braces. These are so-called wall dampers. Okay. This is a chevron brace. This is here in Mexico City. There's one building with viscoelastics, a brace, and also another wall damper. And if we look back at the history of this material, it was the first damping material used in buildings. In 1969, it was developed for the World Trade Center towers in New York City, where they had some wind vibration issues. And since then, there are some of the tallest buildings in Seattle also have these. And then in the 90s, this moved over to Asia, where the majority of the applications are now in these viscoelastic materials. So right now in the world, there are 50,000 viscoelastic dampers in service and in more than 500 buildings. And multiple buildings have undergone hurricane-level wind and major earthquakes and have performed extremely well. So again, this is the World Trade Center towers. These were some of the people, Davenport, the father of wind engineering, and also Robertson, who was the main structural designer of this building. And basically, they pioneered this, and there were over 10,000 dampers in these buildings. So one of the things that I'll show you is that our developments in the last 20 years, we can achieve what they did with 10,000 dampers with about 100 dampers now, because of the way that we configure them and because of the force that we can generate in the damper. These were very small dampers. You can see here the size of the damper, just 2 layers of viscoelastic material between steel, and they were positioned on the perimeter between, they had beams from the core to the perimeter, and they were positioned on the bottom chord here. So when this building swayed laterally, there was a deformation in the bottom chord, and this deformation was generating the movement that was then inducing the viscoelastic material in shear and adding the damping. This building was monitored, and it was confirmed that it added about 1 to 1.5% damping, which is what they required for wind vibrations. And then also the tallest building in Seattle is the Columbia Seafirst, and this is also a very similar damper. And you can see here that they're using some sort of outrigger system, and the dampers are activated by the vertical motion caused by the core moving relative to these outrigger columns on the outside here. So these buildings are all still in service right now. And then some other things, some retrofits. We've been discussing here with some of the colleagues and some engineers how you have a lot of old buildings in Mexico that require retrofit. So this is a great retrofit strategy because the dampers provide both stiffness, so they can also fix irregular problems of the building. You can use the damper as a spring and offset existing irregularities, and then you can use the added damping to reduce the deflection such that these non-ductile frames do not fail during the earthquakes. So you can see here similar applications. These are the headquarters of 3M in Mexico that have these chevron-based dampers. So I'd like to focus a little bit more now on some of the issues that we are now focusing. The technology has been developed. I will show you some testing as well. But also, what are the types of problems that we're trying to solve using this technology? And so I want to look a little bit at some of the problems that we've faced and worked with structural engineers on solving dynamic wind problems for very tall and slender buildings, and also looking at the seismic response. So the question is, how do we take advantage of these really good properties of the material? And in general, for seismic loading, we have relatively short durations. You know, it can be 20 seconds up to a few minutes if it's a subduction earthquake. We have large amplitudes, multiple modes of vibration, multiple frequencies. It's very infrequent. And the dampers, you know, ideally would work for the frequent earthquake, which we are now designing for in US and Canada, the design level, and basically the maximum credible event, okay? So then if we look at wind, the loading is very different. In wind, we are looking at storms that can last up to 3 hours for the peak, and sometimes with 6 hours of buildup and 6 hours of post-storm. We have large amplitudes only in the fundamental modes. There are no higher modes in wind. We have a combination of quasi-static loading. So we have a static, a background quasi-static or quasi-dynamic, and we have a dynamic effect, and the three together combine to form the dynamic loads. The big storms are also relatively infrequent. And right now, except for our system, dampers are only used for 1 in 1 year and 1 in 10 years serviceability. So because the damper is reliable and is a distributed damping system, it is now being used to reduce wind loads also under ultimate limit states. And I won't talk today about this, but we also have a lot of applications where we are using it to damp out footfall vibrations in long span floor vibrations. So for you, it's not hard to convince you, but sometimes we give presentations in places where people don't believe us that buildings move because they're so massive and big. So every time we find videos, this is a building in in Hong Kong during a recent hurricane. So we work a lot with hurricane, and you can see here this building moving quite a bit. You can see the size of it. It's probably a 100-story building. And they're swaying, you know, maybe 1 meter, 1.5 meters in these storms. So we really have, these are real vibrations that we have to work with. And some of you may have seen this. These are buildings moving in Tokyo after the 2011 Tohoku earthquake. It's about 300, 400 kilometers away. This earthquake also revealed some very long period content in the earthquakes, which affected these buildings. And again, these are dynamic structures. So talking a little bit more about the type of problems we've been brought to help solve as well. This is basically a building from Chile. And one of the issues that we face, and I think in Mexico, you're using conventional construction almost at 100%. So you are going to expect severe damage during the earthquakes. One thing is to get damage at the base of the buildings, which I think we expect were the plastic hinges. But really what has rendered a lot of these buildings uninhabitable and have been demolished for it is the distributed damage and coupling beams. So these beams are very stiff. They tend to attract a lot of damage. And the bad news is that they go from the bottom all the way to the top. And so you will have every floor with these types of damaged concrete beams. And so then the whole question of post-earthquake response becomes extremely important. We don't realize as structural engineers that it's not just about the structure. There are people here, there's an owner, renters, somebody has to make a decision whether this building is safe to reoccupy. We don't have instrumentation, so we have no idea what kind of ductility these elements have undergone during the earthquake. And therefore, there is sometimes, if you look at the example of New Zealand, you'll see that 10 years after the earthquake, there were still litigation on more than 50% of the buildings. They did not know what was the proper course of action. So all of this affects quite a bit. So I mentioned New Zealand. You may already be familiar with this, but with very modern codes, they had 80% of the 50 tallest buildings were demolished, even though only one building was collapsed. So you can see here, imagine in downtown area where you have such percentage of buildings that have to be reconstructed, just the global impact of seismic damage. So another thing that we have dabbled a lot, I mean, the tallest buildings we've worked on are about 650 meters, but we also do a lot between, 50, 100, or 50 and 200. And the other thing that the Council of Tall Buildings and Urban Habitat has recognized now is that the levels of damping of buildings tends to drop very quickly as the height goes up. And the mechanism for this is not very well understood. Some people believe that it's related to the way that the non-structural elements are stressed during vibrations, and as you get taller, you get relatively less of that frictional contribution to inherent damping. But now, since the 2000s, they have revised. They used to use 2% or 5% for wind, and now for these tall buildings, they're using, in many cases now, 1%, 1.5% damping. So this is now also making the problem more severe, because with the lower damping, we are seeing enhanced dynamic response. So the other thing, I don't want to do a long lecture on this, but this is a very important topic, inherent damping. Again, this has come to the forefront with tall buildings because we've observed with measurements that they do not have the levels of damping that we have been assuming for low and mid-rise buildings. And there's very little good data of the real damping of tall buildings. We know, even from our own monitoring of tall buildings, that it's amplitude dependent. It's also geometry and structure dependent. If the structure is behaving more as a cantilever, the damping tends to drop. If it's behaving more as a shear frame, the damping tends to be a little bit higher. And each company throughout the world has internal rules on the value of damping that they use. The wind tunnels will give you sometimes some advice, but ultimately each practice, and that could vary quite a bit. So if we talk a little bit for tall buildings, what are the damping systems that are being used? Right now we have two families. dampers. The top ones is what we call distributed damping. In reality, these are real dampers. So they're really dissipating energy as a result of their motion during the vibration of the structure. And here we have the so-called vibration absorbers. These are not really dampers. They are secondary vibrational systems, which, when tuned properly to the vibration of the main structure, will have the same effect of added damping. Okay, and so you know, our opinion, and we work on solid dampers, but you know, these are significantly more robust systems than these, especially for earthquakes. So these systems here do not get used for load reduction in wind, and they typically, for tuned mass dampers, they basically tend to be locked up during the earthquake because they're worried about the seismic response. So these have the possibility to be used for both wind and earthquake, and these are distributed over the heights, so they have a much more higher efficiency, not only for the fundamental mode, but also for the higher modes. So if you look at the different systems, as we mentioned, we are working or have been working on the solid dampers, which, as I mentioned, is a material-based damping, different than a piston-based mechanical device. And I'll show you some low amplitude tests where you can see here that even at displacements of 1 micron, you have viscoelasticity, whereas these devices tend to be inefficient for the first few millimeters. When the fluid is moving, they tend to have a response, and they tend to be calibrated to the peak displacement. And then also the vibration absorbers here. So one of the things we did in the early 2000s with Nippon Steel Engineering in Japan and with 3M is that we developed a way to stack a very large number of these plates together. You remember the examples that I showed you a second ago in the World Trade Center in Columbia, the Columbia building in Seattle, where they had 2 layers, and so it's quite limited the type of force and stiffness that you can develop. So by stacking these and being able, we can go up to 30 layers, and these can be as big as, you know, 400 by 1 meter, so 400 millimeters by 1,000 millimeters. So when you start adding the effect of each one of these very large areas, we are starting to develop some very large forces, and I'll show you some tests. We are even designing dampers now for 10,000 kilonewtons for one device, okay? So this may look like a rubber, it may look very soft, but when you combine it in very large areas and in parallel, you can really create some very efficient loads. I'm not going to get on the material side too much, but we are using a very classical sort of linear damping material currently. But as I mentioned, aerospace and automotive have really advanced a lot. And now, just based on the chemistry of the polymer, we can achieve basically velocity limiting materials and also elastoplastic materials, which seem to be yielding like steel, but they recover all their properties again. So we have also a degree of freedom to work on the material side with the material engineers, the polymer engineers, to change the properties of the polymer. I'm going to really focus on this one, which is the one that has been the most applied. But you can see some tests we've done in the lab here. This would be a linear material. This would be more elastoplastic. You can see here in a velocity limiting here, and then again, plastic velocity limiting, so we can really play around with some great properties, and it's all happening at the molecular level. So the material itself, before we bond it to steel, will come out in sheets like this for the size that we need, so it's manufactured like this, and then we peel it off and we bond it to the steel. And really the family of materials that have been used, the acrylics, we have high damping rubbers, butyls, and silicones. And, you know, I would say that the acrylic is the superior material. We work primarily in this. This has incredibly good aging properties. It's an inert material, unlike damping rubbers, which basically can continue their chemical reaction over the life of the building or the use. Acrylics are basically inert materials that have excellent long-term property and fatigue properties. So how do we use the dampers? Some of the configurations that we have looked at, some are wall dampers. So this damper is activated with horizontal motion when the frame is moving. We have coupling beams, outriggers, braces, and in Canada and the US right now, timber is becoming very popular. So we're also doing shear walls made out of timber that have dampers all along the height. And finally, I mentioned this previously, we're also using some floor vibration dampers by installing viscoelastic material between the beam and the slab, which increases the damping of the floor to reduce vibrations. So now if I focus more on what we've done in concrete buildings, we typically apply these in coupling beams between shear walls and in outriggers, okay? And you can see here, this is the kinematics or the mechanics of how it works. This is a building that has 20 stories of coupling dampers here, 20 stories of conventional coupling beams, and another 20 stories of conventional on top. And you can see here that when the building is swaying horizontally, this is inducing relative motion between the two walls and is then inducing also the damping shear or the shear deformation, which is then damped. And then here, if I illustrate, these are real projects that we've done. So I'll show you a little bit more pictures later, but these are some animations. So this is an outrigger project. And you can see here that as the core is moving relative to the outrigger column here, we are producing again the relative motion and adding damping to the structure. Of course, the motion is exaggerated. Typically, it will be fractions of millimeter under wind, maybe 5 millimeters, 4 millimeters under ultimate wind. It will be maybe 3-5 millimeters under frequent earthquake, and it can go up to 20-30 millimeters in a large event. So you can see here the coupling damper installed in a building, and you can also see the coupling damper installed in an outrigger, as this is the factory where all the panels are lined up before they get shipped to the site. So let's talk a little bit about what is our design strategy for buildings with these dampers. And what happens is that depending on the application and the location of the building, there will be more emphasis on wind or earthquake, and then sometimes in both, okay? So the general thing is that during wind loading, all the deformation is carried viscoelastically in the damper that is installed here. And for moderate earthquakes. And when we get a very severe seismic event, what we do is we allow for minor yielding of the steel plates that are connecting in order to limit the maximum forces which the designers are using to design the walls and the outrigger columns. So this is the way in general that this is implemented as a dual loading device, both for wind and earthquakes. Okay, so for wind loading, if you look at tall buildings, you will find that the total, let's say, base moment in the X and base moment in the Y is a contribution of a mean portion of the wind, a background, and this red portion, which is the resonant, the dynamic portion of the wind loading. And you can see here that for some tall buildings, this is dominating the peak moment that you have to design for at the base. So this affects your foundations, it affects your wall sizes, etc. And we know that this dynamic portion, the red part, can be reduced by 1 over the square root of the added damping. So our added damping tends to have a very significant effect on the basically wind-induced vibrations. So you can see here that if I look at added damping for very tall buildings, and I look at the MY, the moment about the y-axis, okay, you can see here that as I go from 0 to 2, I'm dropping from here to here. And if I provide, like if I get, to 6 or 8% damping, we are basically going from 5 to 2. So it's a major reduction of the wind loading. For seismic, typically when we replace coupling beams of a conventional building with viscoelastic dampers, the building will tend to soften a little bit. So the period will elongate a little bit. And what happens there is we tend to get a drop in the demands. And of course, when you increase the period, you tend to get an increase in displacements, but we are using the supplemental damping to control displacement. So by using the damper, we are getting a damping effect, and we're also getting a period effect without increasing the drifts, which we have to, of course, maintain in control for damage control. So just to summarize what we are doing, basically for all wind loads and for frequent and design level earthquakes, all of the response happens in the viscoelastic material, and we are reducing accelerations, drift, velocities, and forces because of damping. The behavior is viscoelastic, and there's literally no damage. So this material, during our seismic design, strain of 300%. So 3 times the thickness of the material is the allowable strain that we design for. The material fractures at about 600 to 700% strain. So we do about half of that as our working. Now this material can do 4,000 cycles at 300% strain with less than 10% reduction in stiffness and damping. So it has a tremendous ability. Never in an earthquake will this material basically lose its properties because it just has tremendous fatigue resistance. And of course, we are always looking at cost-effective designs, increased sellable space, and material reduction as a result of the added damping. And then in the maximum credible earthquake, which, by the way, we predict, but we may also underpredict, can be larger than what we assumed, the system has a fuse-type mechanism which allows for minor yielding of the connections, which then will allow for a fuse response that will stop the increase of forces. Okay, you can inspect the steel, and if it is damaged, you could replace it, but the demands on the steel typically are quite small and do not need to be things. So let's jump into some testing. I think testing is always better to see. So we've done tens of thousands of tests over the last 20 years, ranging from material tests to larger material tests, to shear tests with real concrete walls, and also to large-scale testing of dampers. So I'll show you a few of these tests just to get an idea. So as I mentioned, we start with material. We understand the material behavior. We calibrate our numerical models. Then we go to full-scale dampers in the axial direction. And then we get this, and then we put it into the system with realistic boundary conditions to see how it will work in a real structure. So before I show you some of the tests, I want to come back to this difference that I mentioned between viscoelastic solid and viscous dampers. And the difference here, as you can see, I'm testing in the lab here. I'm starting at 8 millimeter cycles, and I'm gradually decreasing the amplitude. And you can see that as I go down to 1 millimeter, half millimeter, and down here I'm down to 1 micron level. This noise that you see is just the instrumentation in the machine, but you can still see very clearly that I'm getting the viscoelastic response. And this is why I can use this material for the 1 in 1 year wind for serviceability, 1 in 10 year wind for drifts, because I know that even at very small deformations, it's going to exhibit the viscoelasticity that we are relying on. So here is one of the large tests. So you can see we built these walls. This is sort of a rotation point that we have here, another wall here, the damper here, and you can see these walls are post-tension, so we were able to test multiple specimens by testing and then removing this specimen, putting a new one in, and reusing the top and bottom walls. And this young man here is this gentleman here when he was a student, and his dampers were about the same size as him, so pretty big specimens. So if we start off just to see how this responds, so let's look at wind and low-level earthquake. So you're going to see that we're applying the load up here. This load will rack these walls, and the racking motion will induce the vertical thing. By the way, these are just aluminum arms for the instrumentation, okay? So this is nothing here. This is the damper here that we are testing. So you can see here that during wind loading, we are loading in the fundamental period. There's only one frequency. And if we move now to seismic loading, this is an 85-story building that is modeled in LA under the Northridge 1995 earthquake. We modeled the building in a nonlinear model. We took the time history of displacement through the damper, and then we applied this time history to the whole system to induce the damper deformation that our model was predicting. So you can see here that at this level we get some minor yielding, so we are losing the perfect elliptical shape. Why? Because the white here, these two steel fuses, are just mildly yielding to cap off the forces. So I want to talk about this project because the next tests I'm going to show you were done specifically for this project. So this is probably the tallest building in the world in a high seismic area, so it's about 640 meters. It was designed by TT out of New York City. And basically, the forces in this building were so severe that they approached us to try and come up with a solution where the damping would help them to reduce this. So we basically removed over 120 stories, all of the coupling beams in the middle here, which is the most efficient location, and we replaced it with our coupling beams. And we then ran time histories, and of course these were some of the largest dampers we had ever built or designed, and part of the project was to test this. So before I show you the test, I want to show you what the dampers do to the building. So those of you who have worked with tall buildings, you're going to see that higher modes, which is this spaghetti motion that you see here, they will induce an amplification of the shear forces in the building. And what the dampers do is they cap off those forces and they break down the higher modes because of the damping. And because the damper works in all frequencies and all modes, you can see that this is responding primarily in the first mode, and we have really killed off the higher mode vibrations, which tend to dominate the shear forces and vibration forces. So that damper that you saw in this building was then designed and built. And at the University of Toronto, we designed this setup to be able to test this damper. So we took the damper, which is used horizontally, we flipped it vertically, we attached it, fixed it to the bottom here, and we also fixed it to the top, and we are applying the load at the inflection point. So this is simulating a fixed condition, and we are reproducing the conditions. We did a lot of finite element analysis to analyze the boundary conditions, and this setup is reproducing the similar stiffness and boundary conditions as that. And you can see here that the loads that we're applying are about 2,000 plus 2,000, 4,000 kilonewtons in this test. So this is just an illustration, one of the students with the damper and the steel links, and this is the main lab. And you can get an idea here of the overall lab. So you can see the actuators moving here. We are applying from here to here the displacement that we measured. And of course, the damper is responding from here, which would be the concrete wall, to the other concrete wall here. Okay? So if we look a little bit closer to get a better view, let's look first at rare wind. So this would be an ultimate limit state wind load. And this is what the wind tunnel analysis told us the damper would have to see during, right now they're designing in the US for 700-year wind. So this would be the response of the damper under 700-year wind. And you can see that the frequency, there's only one frequency, which is the fundamental frequency. But of course, during the wind loading, the amplitude changes. Okay, so this is a real simulation of the wind load that was given to us by the wind tunnel. in order to simulate an entire storm. So we use the damper to do 12-hour storms. So we had build-up, peak storm for 3 hours, and post. And we can see very nice fat hysteretic loops here, very stable. And of course, no deterioration or any damage. And we also do characterization tests at every frequency to calibrate our models. So you can see here we are moving the damper up and down. You can see the shear layers that are being sheared. You can also see here the parallel plates, how as we add layers, because we intertwine them, that we are getting half the plates moving in one direction and the other half moving in the other direction. So if we go to the more interesting stuff, of course, we love to break things in the lab, and we paid so much money to build this setup, so we weren't going to stop until we failed the specimen. So we went to higher and higher demands, which are way beyond what the system would be designed for, but we wanted to understand the failure and the ductility of the system. So you can see here at 50 millimeters of displacement from this point relative to this point, we get minor yielding. At 80 millimeters, we get a little bit more. At 110 millimeters, we can see the yielding is severe. At 140, and I believe it failed at about 200 millimeters of displacement. So this is an actual Tohoku event run on this very tall building, 85-story building. And you're going to see here that in this event, this recording, we're getting low amplitude vibrations. And then you're going to see after, it's almost like the earthquake was 2 earthquakes. After this first phase is gone, we're going to see a pulse hit the structure, which of course is going to go, so all of this is viscoelastic, so we have no damage in the structure. And then at some point, this pulse arrives, which is going to drive this system into the inelastic range. And we're also going to see that it caps off the forces. So this is starting, this is the pulse that's arriving. So again, the yielding here is quite minor. The role of the steel is not to dissipate energy. The energy is being dissipated here. It's more to cap off the forces. That's the role of this, you know. So in the last, so of course, I'm going to talk a little bit about this, but resilience, you can see that this damper can undergo multiple dozens of MC records, and you would expect the concrete beam to be like this after one event, you know. So there's a big resilience difference, obviously, here. So here we want to break the system, so we continued pushing and cycling until we can fracture this steel. And before we did that, this will illustrate, remember the little animation I showed you on the intent? Now we're going to reproduce it experimentally here, so you can see live. So this is 0.5 millimeters. And then we go to 1 millimeter, all viscoelastic, 4 millimeters. 7.5, 15, 23. At about 30 millimeters, the system stops moving in the viscoelastic, and we start inducing yielding in the section. So now we are at 120 millimeters, or 6% rotation, 220 millimeters. %, rotation in the system. Conclusion from this: steel can be very ductile if you detail it properly. And you can see also here that for designers of very tall buildings, they need to know that there's a true cap off on forces, because my outrigger columns especially, if those are overloaded, they can buckle and the whole outrigger system can go away. So I'm not going to get into the modeling too much, but we have models that have been developed and validated. Of course, the most simple model is to use a spring and dashpot. These are developed for a single frequency. We then combine this with a yielding spring to get the inelastic element. And this will give you the one mode. We also have developed our own thermomechanical models which predict the heat increase in the viscoelastic material. So you can see here experiment and our theoretical equations track it. If we are not happy with the increase in temperature, we will then increase the thickness of the damper to reduce the strain and induce the self-heating to control the properties. So this is something that is very important. So you can see here that these models are implementable in Perform 3D, ETAB, SAP, OpenSeas, Abacus, LS-DYNA, and other programs. And you can see that once you calibrate it, the red is our Perform 3D model and the black is the experiment that we just saw. So for one frequency, it's quite easy to do, but then we've developed multi-frequency models. So you can see here experiment versus numerical, and in here I have first mode, second mode, third mode, and so the model is capable to capture all of these. And all of these are implementable in ETABs, so it's not very difficult to actually gain capability in ETABs to be able to model what this damper can do for your structure. So for the wind testing, this is what we did on this project here. So the wind tunnel in southern Ontario, close to Toronto, RWDI, did a wind tunnel of our building. We then got the time histories from the wind tunnel. They were applied to the model. And then from there, we tracked the VCD response. You can see here, I believe this is the time here in hours. Maybe not, maybe minutes, but it was a hours. Okay, so this is a big storm. Then from there, we applied this to the damper, the time history that came from here. And from here, we can check our model, and we can also check our thermomechanical model to see if we are predicting the heating of the damper properly. So this technology is marketed by Kinetica. Mike is the chief officer of this company, and I'm going to show you a few building applications that we have done. So this is a 200-meter tall building, very slender, 1:12 aspect ratio in one direction. And this is the building here that I showed you. So the way that we do this is we build, use steel embeds. Let me stop here if I can. Yeah. So when we install the damper, what we do is we embed a steel section inside the concrete wall with a steel placeholder, and this is just an example of this section being craned in this site, and it's dropped in. Then we basically will level it. And then they will cast the concrete. Then they will cast the slab. And they just keep on going like that. And then after or at any point in time, a second crew will come back, remove the steel placeholder, and install the damper. So this way the damper is not on the critical path of the construction. It's not bothering the contractor. And you can see here, this was the installation crew. They just, built a jig which goes up, picks up the steel section. And this can be done at any time. It can be done 2 weeks after the beam is cast. It can also be done right before drywall is done. So this is the steel section removed, and then they just lift the panel in place and they bolt it. It's a normal bolted steel connection that connects it. And because the material does not require inspection or replacement over the life of the building, the architects can come and box it in like a concrete beam. So you don't have any impact on the architectural layout of your building because you're removing a structural element and you're putting the damper inside the location where the concrete element was. So you can see here this is installed, then drywalled with metal studs, finished and painted. So it's not even visible at the end of the project. Okay, so this is another project, 2 towers, 71 and 46 stories. And here we took advantage of another thing. Because these are 2 buildings linked together, we used a so-called buttress system where the interface between the 2 buildings are the ones where the dampers are installed. So as the buildings move relative to each other, they're coupled, of course, in those locations, but we are getting an excellent location to damp out the vibrations. So these are some of the most demanding projects. This is in Southeast Asia, where we have basically these 4 buildings here that were designed by Arab are basically in Manila. Manila has the wind loading of the city of Miami, hurricanes, once a year approximately, and it has the seismicity of Los Angeles, a bit higher than Los Angeles. So there's a fault about 3 kilometers from this development. So this was a very challenging project where the technology could help both for wind and earthquake at the same time. So you can see in this case we chose an outrigger configuration. For the shorter buildings we had 1 outrigger, and for the taller buildings we basically had 2. And you can see here we're discussing with some consulting engineers that in Asia the showroom for the condos has a damper room where they're showing the clients who are buying this building that their building is a more resilient building, and they also have a small shake table in the showroom to show them the difference between an undamped and a damped building, and the clients are paying a premium for damped buildings or isolated buildings because of the higher seismic performance, you know. So again, this is Mike here with an outrigger damper. These are installed in the buildings. And then if we move a little bit closer to us in Vancouver, these are some towers that we are currently, these are under construction right now. This one is completed with the outrigger dampers here. Another outrigger project. One thing that I believe here in Mexico City might be quite relevant to you guys, I mentioned this before, is retrofit. So this was an example. This is in Vancouver in Canada. It's a hotel. This is 1970s reinforced concrete frame, which is non-ductile. And therefore, they required a way to upgrade this tower here. And what they did is basically use the dampers in a wall configuration, in some locations in a brace configuration, and they are installing it directly onto the concrete beams, the existing beams, and also in a chevron in the taller floors here. And so this is a very interesting, basically, approach to older buildings. And also because the damper, this is not to scale, but the damper is typically installed quite close to one column. It means that the rest of the span here is not blocked as it is by a brace. So architects and others and owners will appreciate this, and it works just as effectively in that configuration. So the last thing I want to show you here, these are some hospitals in Canada, and what we are finding, I know that your Mexican code in the last iteration, your seismic loads have gone up, which has resulted in bigger walls, bigger coupling beams. The same thing has happened in Canada on the West Coast, in Vancouver. And you can see here that what we are observing in these buildings is that the walls are getting very big, 1 meter, 1.2 meter thick walls. And we also have some very large coupling beams which are 3.6 meters by 4.2 by 5 meters, or sorry, 3.6, 4.2, or 5 meters by 1.5 by 1 meter deep coupling beams. And these are diagonally reinforced, so very hard to build, very big delays in construction to build these. And what we are doing is by installing the dampers instead of these coupling beams, we are getting a lot of advantages. And here is a conventional design, which was then value engineered for this damped design. So you can see we are removing all of these diagonally reinforced coupling beams, and we are getting also a response where we have reduced the wall size from 1 meter to 0.8 meter, and there's also a 25% reduction on the reinforcing steel. So these are actually drawn to scale. This was for this project. So you can see the 1 meter walls, 0.8 meter, and look at the reinforcement ratio, the difference between the damped structure, which is much softer, the loads are lower, but the drifts are almost identical, and the more heavily reinforced. And this is the erection process that was developed for this project. So we have a steel section with a steel channel, and basically we go in, the steel beam is dropped into place. The American code has guidelines for how to do these zones to maintain them, according to code. And then you basically cast the concrete, and after that you install the dampers here. And these are some details in the US and Los Angeles. You can see how the coupling beams can be dropped in here. These are steel beams that can be dropped in, so this is saving a lot of time. And you can also see here, just so that you have an idea, I think the consultants in Mexico here told us that you don't do this. I recommend you don't do it because it's incredibly time consuming to actually weave these huge bars in diagonally. As you know from the code, you cannot splice these bars, so they have to lift it from up here. You see the bar here? He's trying to push it in through the coupling beam and through one zone and through another zone here. And we have designed or seen in some of our projects coupling beams with 135 M bars per beam. So you can imagine the time constraint and the delay that this process is bringing. Okay, so I'm going just to conclude in this last slide, because I've worked many years now in dampers and isolation. I really like to, and a lot of young engineers are very excited by these technologies. I want to really bring up some things that I believe have to be front and center. When we approach and somebody says you're going to take a damper, you put it in the building, as a designer and as a modeler, you are thinking, great, I can put a C value inside the building and this is going to reduce, everything looks positive. But really the implementation of these technologies, they hinge around these questions. And very often structural engineers either do not ask these questions or they ask them so late in the project that it's impossible to backtrack, okay? So every technology, you have to understand the reliability of the technology. What is the maintenance requirements, tuning, monitoring, in order to get a reliable damper, especially if you're using it for strength design. You need to basically know the reliability for different load characteristics. We see very often people putting it in for seismic, and they have given no consideration that this device will undergo millions of wind cycles, and then we see leaking devices, other problems, and all that. So you really have to be careful with these things. Then, as structural engineers, we only look at fatigue for very rare cases, something that is very wind sensitive. But for buildings, very little analysis is done for fatigue. But these are devices. You have to look at fatigue. You cannot jump this step. And this has to be looked at very carefully. Sometimes for wind, you need to work with the wind tunnel to understand what is the lifetime loading over 100 years of these devices. As the small amplitude sometimes. And of course, we know that these devices will be moving even a very small amount. Also, the long-term behavior. As a structural engineer, you're designing buildings for 50, 100 years. What is the robustness of the supplier's long-term behavior, data? Okay, is this reliable or not? And also, do you have components in your system that could over time fail? Okay, so we have pistons, they have seals, high pressure, high temperature, so you have to be sure that this will work over the long term. I talk about redundancy. Is the system a binary system? So if you take a viscoelastic damper and you start loading it, okay, what happens when it fails? I'm not showing the fatigue tests we do here. What happens is at 5 million cycles, you will lose 5%. At 10 million cycles, you will lose another 5%. So you have a very gradual failure of the properties. What happens to a hysteretic damper when you fail? If you fracture the damper, it's binary. You have 1, it works. Fracture is 0. You have no redundancy. What happens to a fluid damper? You have the fluid moving. If you break the seals and you lose the fluid, there is no intermediate response. It goes from 1 functioning to 0. So these are aspects of robustness that if you're really seriously looking at 50 to 100 year implementations, should be at the forefront, not as afterthoughts. In terms of validation, again, the gold standard remains full-scale validation. So if you do not have full-scale validations, and especially with proper boundary conditions, you as a structural engineer should really be very careful with that. Model validations, which I think are pretty common. And then the analysis framework. What is the complexity of the model that will yield results that are relevant? Okay. Sometimes the very simple models are fine, but sometimes you need to go and increase the complexity of the modeling. For example, for us, thermomechanical is necessary because for us internally, we need to know how much this damper is going to heat and what is the effect on the properties. And basically, we need to gradually build this, but also not to burden the structural engineers with extremely complex models, because when we do that, then they will not be able to implement it. So this balance in modeling is very critical to allow for the implementation of these technologies. So this is all I had. Thank you, and I'm happy to answer questions if you have some.
Vamos a abrir la sesión de preguntas, primero presencial y luego tenemos en Facebook y en la otra red, no sé qué se llama, pero hay como 100, YouTube, hay como 100 en línea. So, primero vamos a ver con ustedes, por favor. Puede ser español o inglés. Profesor Christopoulos, habla bien en español.
Bien, no sé, pero... Yes.
I only have 2 questions. Do you consider also out-of-plane differential movements between the plates? Are they just flexible enough, or is it not necessary in this case?
They have capabilities. For example, some of the testing that we did, we had up to 20 millimeters of off alignment with the walls. So during the test, we measured about 1 inch of this. So it has the ability to bend and to absorb some level of that. Of course, this is not a desired way to use it, but when we run full models of buildings, the coupling provided by the slab really minimizes that. So when we actually run real buildings, we do not see things. So the damper will move out of plane, but the walls tend to move together because of the diaphragm function of the slab. So we see maybe fraction of a millimeter of differential in this, or twisting. We don't really see it.
Perfect. That's just a follow-up question, since you mentioned the slabs. Do they require any details to provide like movement capacity vertically, or
yeah,
so
that's
that
a great question.
Okay.
So what we do is, as you saw in the testing, we leave a gap between the device and the slab. So the slabs are thinned out over our device.
Right.
So to a minimum, and of course the device is only 1 meter by that, so you really need a minimum slab just for the loads that are local. And then what we typically do, if the slab is very thick, we have some projects where they use huge slabs, what it does is it's competing in parallel with our damping system. And what it does is it's sucking out. So for the same damper, it's like you're probably familiar when we have a viscous damper and you have a brace. The elasticity of that brace is making your efficiency go down. So we typically like to make a joint on the two sides.
Right.
In some of the projects, what we will do is introduce a thin aluminum reglet in order to create almost like a hinge. And we run the rebar right through the middle, and then it goes up and down, and we create that. To be honest, the contractors don't like us to be, put this reglet. Those guys are brute force, you know, they really get upset. So what we've done in a lot of projects recently is they cast it, and we come back and we saw about 1 inch or 1.5 inches, and we've shown with some analysis that it cracks right at that saw, and then it moves vertically. So if you create that, as long as it's not competing with us. Now, Arup and MKA have their own slab details. Arup likes to completely isolate the slab on the outriggers. So they have, maybe you caught it, I had a picture with two beams around our damper, and they had a slab, and they have it like completely isolated. And other people have developed their own details. So that what we tend to do is we tell them, be careful. If you don't do this, you have to model the stiffness effect and discount the damping that you have in there.
Right. Thank you. Thank you.
Welcome. Yes?
I have a very simple question. How is the interaction between this slice of polymer and the steel plate? How do you connect them together? With bolts, or do you have to use a special glue?
Okay, that's a good question we were discussing over dinner last night. So in 1969, in the original World Trade Center towers, when 3M had basically 6 months to develop the material because the building was halfway built when they realized they were going to have problems. In that time, they didn't have a bonding method, so they used an epoxy-based bond. Of course, this is not ideal because now I have to worry about the material aging, fatigue. I have to worry of the epoxy to viscoelastic bond, and I also have to worry about the bond of epoxy to steel. So the first generation of viscoelastic materials developed by 3M required a bonding agent. Now, we are currently using the 4th generation of this material. So in 69, it was the ISD 108, 109, 110, and now, 108, 109, 110 was developed, 110H, 111, 111H. So we have the latest one. Starting in 2000, the material became self-bonding. So it has a tackiness. So if you apply one layer of the material on top of itself and you apply only pressure, the material will bond, and this bond will become stronger than the material itself. And on the steel, we have a special preparation of the surface, which is a roughening. It's sort of a sandblasting, but it's more the sandblasting that they do in mechanical engineering. It's not the typical sandblasting that we do in structural. So it's a different pellet, and it has a different surface. Then it's cleaned. Then they use something to neutralize the electrical polarity of the surface, just a liquid. And then the material just bonds on the steel. And we use pressure. And again, this is stronger than the material because think of the sandblasted surface has, let's say like this, mountains, okay? The material is going to flow inside these deformities and is going to form a double bond, chemical, like a glue, plus mechanical, which is thing. So the steel, we have some, we do tear out failures. So every time we do a project, each batch, we will do some tests before they start production. They pull and they fracture the material, usually around 700, 800, 900% strain. You will rip the material, and you'll see that it's never in the bond. It's always in the middle of the material. So the good thing about self-bonding is I only have to worry about one material now. It's the viscoelastic. So I can do tests on aging, fatigue, and all that. This is not going to deteriorate or interact with another chemical.
Well, a second question. You were telling us earlier that there is an increase of temperature.
Yes.
Do you think this can affect the system?
Yes. So what happened is, again, remember I mentioned it, we are in the 4th generation. The 1st generation was quite sensitive to temperature. Basically, it was heating up very much, and we had a very large drop of stiffness. What they did gradually is that the sensitivity to temperature has been reduced a lot. And the other thing is, as I mentioned, so let's say my design earthquake requires 30 millimeters of displacement. Okay, so I go back, I know that I have 300%. So 30 millimeters divided by 3, I will use a thickness of 10 millimeters, because that means when I go to 30 divided by 10, I get 300%. Okay, now if I predict that during this loading, I don't like the temperature rises too much, what I can do is I increase the thickness and I increase the area to compensate for the loss of stiffness. So I can get the same damper, but with less heating by increasing the thickness. Now, in all the tests we did with the latest material, we are observing in the worst earthquake, maybe 2 to 3 degrees temperature rise. So in earthquakes, this is not an issue at all. Where this is an issue that we are very careful is ULS, wind force reduction. Because this storm can start for 6 hours. So imagine you're going 10%, 15%, but it's hours, you know? And that's why we need to understand over the windstorm that the wind tunnel is giving us, if this is somewhere more than 15 degrees, 10 to 15 degrees, we then redesign the damper to reduce it. So we like to stay within plus 10 degrees Celsius, not more than that, when we design the damper.
Thank you.
You're welcome.
¿Otra pregunta?
Thank you. How effective is this system to protect content? For example, I saw that you install it in healthcare buildings, so how effective is it? And if I compare it with base isolation, what is the benefits?
Yes. Yeah, very good question as well. Okay, so of course the damping will reduce accelerations, because if you look at any spectrum, you increase damping, you see the acceleration drops somewhat. So this is, let's say, the most simple thing. So we will affect accelerations. I think the real advantage is that when you look at a loss analysis to take into account the losses that are coming from non-structural and content, if you do the study, really the more frequent earthquakes are really dominating this, because the frequent earthquake is very likely to occur. And that's why, and also the conventional structure during a 43-year or 50-year event will not yield. So you have an elastic structure where you get the amplification. The advantage we have is that even at the 1-in-1-year event, this will add supplemental damping. When it becomes nonlinear, a coupling beam may produce a lot of damage, okay, but it's a very ductile and very good system. Okay, don't get me wrong, I'm not saying that coupling beams don't work well. They work very well, very ductile. When they go, they also cap off accelerations. So we are a little bit better than them in the ultimate event. But the real advantage comes for lower events, because we are adding to your elastic damping. And that is helping a lot. So we've done some studies on some of these buildings where we looked at really integrating the losses, both non-structural, drift dependent, and content acceleration dependent. And we saw that there's really a lot of benefit, especially in the more frequent earthquakes, so below the dBE, you know. The other thing I would say is, you remember in the healthcare facility that I showed, one of the problems we have in Canada is that they came up in 2024 and they said that the structure for post-disaster must remain elastic under the 1,000-year event. Okay, so now the size is no longer dominated by MCE divided by R factors, but it's this elastic condition that it increasing the elastic design of the structure. What that happens though is this stiffness increase, we see a huge increase in accelerations. And the structure is so over-designed that it's remaining elastic, you know, for very large loads. So now, because we are using the damper to reduce the strength of the structure, so it's becoming softer, we see a period-dependent acceleration drop in addition to the damping drop. So we see a big difference there, but this is because of the strength, not because of, you know, the acceleration. But of course, for every project, you have to study this. The problem we have, I believe you have the same here in Mexico, is that the owners, even hospital owners that we've met and talked to, even though they claim, yes, we prefer a less damaged structure, they are not telling the engineer from the very beginning, this is a criteria for us to judge your design, right? It's an afterthought, you know, right now. So it's very hard to convince them on non-structural elements. You're welcome.
¿Alguna otra pregunta? Vamos a leer un par de preguntas de quienes están asistiendo en línea. Una es, profesor Christopoulos, ¿cuál es el criterio de dónde colocar los wall dampers? Where the wall dampers are placed on the structure? How do you select the locations?
Okay. I'll answer in English. I understood the question, but I'll answer in English. Usually when you add a damper, and especially in a retrofit, one thing that I didn't discuss, which is a bit of the challenge, is that the damper will produce forces. And those forces have to be connected to the structure, and they have to be resisted by the structure. So when we are adding the dampers, we are going to try to add them in locations, the wall dampers, where we will minimize the amount of strengthening required in the structure. So typically, we will put them close to one column because the rigidity of the column in flexure makes the damper work more efficiently, for one. And then we are going to decide how many dampers we put per floor based on how much force the columns and the beams of the existing structure can resist. So if they are very weak, then we have to put multiple dampers so that the force per damper is low. If the strength is decent, then we will try to minimize, to try to reduce the cost of the dampers that are implemented.
There is a question about the cost of, they are curious on the tested of the specimen. How much costs the one with the walls?
I think the cost is very variable. You know, I mean, I can give you a range. It can be as low as $5,000. It can be some of the giant ones were, you know, $20,000. It's very, very variable. I think typically the cost, you know, I can tell you what factors affect the cost. Obviously, the volume of viscoelastic, the number of plates, the number of layers, the size, you know, all of that will play into it. But I think typically, you know, the cost for us is always a question of making a solution which is more economical for the owner. So I think there's always weighed against reduction in concrete, reduction in rebar, reduction in construction time, and very rarely do we do projects where resilience is the main thing. So I would say that in most cases, we're able, with optimized designs, to get to structures which are also either equally or more economical than the conventional design. And then as an add-on or bonus, you have the resilience aspect of it, you know. But in terms of cost, it's very hard without knowing the structure, the size, all this to predict that, you know.
Okay, quizá la última pregunta. Last question on the people on the streaming. Somebody is wondering whether there is a special issue on the detailing and performance when you have the steel beam and the wall, when you connect the steel beam and the wall. Is it some special issue?
Yeah, so, I mean, you know, we did not invent embedded steel beams and concrete. This has been around for decades for concrete structures. And very recently, they wrote a guideline, and they tested at UCLA in Los Angeles 4 details for embedded steel beams. So if you look here, what I'm showing in here, so these details are now codified in the US. So these details, they take into account the moment, the shear, and they also take into account the zone reinforcement that is required in order to ensure that the wall is not negatively affected by the embedded piece of steel. So I would say that there's nothing different than conventional embedded steel. And you can see here, I don't know if I can zoom in, there's not a very good, but you can see here all of these details. Maybe, Mike, what's the guideline? Do you remember?
Yes.
AISC? Yeah, the steel code has developed all of these details here. We just copy-pasted them from there. And you can see, you can use rebar for the zones, you can use different details. But I would say, to answer the question, it's nothing special compared to a normal embedded steel beam.
Ok, bueno, vamos a acabar pues esta sesión. Profesor Christopoulos, muchas gracias. Thank you very much.
Thank you.
Our institute is giving you a appreciation for your talk, some souvenir.
Oh, thank you very much.
And this is for Dr. Montgomery, a souvenir from our institute. Well, thank you very much, Professor Christopoulos. Thank you. To you.